Thank you to the organizer for inviting me. So yes, I will talk to you today about optimal transport for graphs. So I have to thank Anna also, who did a very nice motivation for this. And so I'm going to talk to you about related optimal transport losses, optimal transport way to model graph, and to find correspondences between them. But first, I want to thank all my collaborators. I had the chance to have many collaborators on this topic. So of course, Nicolas Corti, with whom I started working on optimal transport, but also many PhD students and colleagues, and I'm very happy to work with them all. Always very nice. You can see here Florence also, who's an organizer of this. And so I'm going to talk today about work that I did with all those persons. Okay. So first, but that's something, I don't need to spend too much time on it, but graphs are everywhere. A lot of data can be modeled as a graph, so social networks, brain connectivity, even 3D meshes. So graphs are everywhere, and we need to process them in a good way. We need to compare them. And so the classical way to do that, traditional way to do that, is to look at the structure of the graph, look at the Laplacian, you look at the Fourier, components of this graph, and then you can basically what you do when you do that, you separate in a way the structure that you look at it from the Fourier perspective, and the features, the signal on the graph. And when merging them together, you can do some signal processing on graphs, you can do a lot of things. But basically, when you do that, you always separate them a little, which is done by GNN. GNN, you extract features on the nodes, so you work on the signal, and then you spread information on the graph using the structure, and then you extract feature again, and you always separate those two steps. And so what we try to do is to look at the graph as a whole object, where the structure and the signals on the nodes are seen together as a distribution. And so if you look at it as a distribution, a natural way to measure similarity is optimal transport. Okay, so what will we talk about? So first, I'm going to do a quick introduction to Gromov-Wasserstein, which was also introduced shortly yesterday. Gromov-Wasserstein and its extension, fused Gromov-Wasserstein. I'm going to show you a few examples of where doing optimal transport between graphs gives you a transport plan, and so that you can align between them. We're going to talk about some relaxations, so extension that can be interesting depending on the applications. And then two parts about, machine learning, using those tools. The first one being unsupervised learning, how to learn representations of graphs as graph-level representation of graphs. And the second one on to train supervised learning methods on graphs. Okay, great. So first, a little bit, a really quick recap, but I like to put the notations there. So this is discrete optimal transport. So when you do discrete optimal transport, so you have Diracs in the space, you have a matrix that contains all the distances between those Diracs, okay, between the source and the target, and you want to find an optimal transport plan, T, that maps, that displays the mass from the red to the blue Diracs, okay? And so in order to do that, so you optimize over T, which is a 2D matrix, okay? This is discrete, everything is finite, okay? And when you sum the columns of T, you recover the marginal on the source. When you sum the lines of T, you recover the marginal on target. This is the constraint here. And you want to minimize the cost of moving from source to target. So it's just a double sum over T is where you move the mass, is mass moving from I to J if T is larger than 0, and C is this cost matrix. And when you optimize that, you recover an optimal transport matrix that basically tells you where the point goes. Okay, so you go from this point to this point, and so on, which is very intuitive and very, makes sense. You can look at that data, look where things go, which is one of the strengths of optimal transport. Okay, so recently, variants of this have been proposed, especially anthropic regularization that allows to have fast algorithms such as Sinkhorn to solve the problem, and that brings also smoothness, because this is non-smooth, this is a linear program, it's not smooth, so in machine learning, when you want to optimize stuff, often smoothness can help. The thing is, this traditional OT, you are in a ground space, and you need a C, you need a matrix C that tells you how much it costs to move from one point to another one. If we talk about graphs, there is no obvious way to say, oh, this node is close to this one or is far from this one. And so the trick here is to use an extension of optimal transport that works across spaces, where now you don't need the points to be in the same space, they can be in different spaces, and if the points are in different spaces, obviously there is no C between the left and the right, but since each points are on their own spaces, they are metric spaces, you can compute distances between the points. So between all the right points, you can compute all the distances, which is going to give you a matrix, okay, the D here, and the distances between all the points on the blue will give you another matrix, okay? So when you have this, you have distributions on different spaces, and you have a metric associated to these distributions. The object is called metric measure spaces. And so you can measure a similarity between the two by measuring how much the distance, the pairwise distance between the point will change after transport. And so you go from a linear problem, okay, to now a quadratic problem. You see the T appears twice because you want to move from IK to JL. Okay, so you need twice the plan, and now you're quadratic, but also now you're non-convex, okay? And that's where a lot of the problem arise. In practice, non-convexity, well, we kind of have algorithms that converge to a local point, and it does work not that bad. Similarly to Synchron and linear OT, you can regularize it. But the thing here is, if you want to look at graphs, you do have pairwise relationships. So you have matrices D. You can take adjacency or whatever. But if you have information on the nodes, how do you encode it? Basically, here it's lost because by using only the distance between the points here and the points here, you totally forget if you do have a connection between those two. Okay? So an example is if you do between two molecules, the atom, the type of atom is of course an information that is joined between the two, okay? You're gonna have carbon on the left and carbon on the right. So you could use this information, but when you do that, you lose it in a way. That's why we propose with Titouan-Vaillé and co-authors the fused Gromov-Wasserstein, where now you have the Gromov-Wasserstein term that aligns the pairwise relationship, but also you add a linear Wasserstein term, and so what it means here is that part of the information is the structure that when you look at just in the pairwise sense, and another part of the information is a feature that is lie in the same space, and where here you can compute a C matrix. Okay, for instance, all those two atoms, carbons, in this case distance is 0. If there are different types, you can put a larger distance, these kind of things. Okay, so I'm gonna show you a small illustration of what you can do with Gromov. So the thing with Gromov, so this is a Gromov, this is a distribution in 2D, okay? Those 2 points are close, this one is farther away, okay? And I can do another one here, okay? So those are very similar in a way, where you have 2 points close and one far away, and if you compute the orthogonal transport plan, this is what you're gonna get, okay? And so I'm gonna rotate it a little bit to show you that the plan is invariant to rotation, which is interesting sometimes in some application. And you see that, so the point that is far from the other one goes to the point that is far from the other one, and the two that are close goes to the two that are close. The plan is actually invariant to scaling here also. The cost is not invariant to scaling because the distance won't be the same, but the plan will not change if you scale. Okay, and so you can do a lot of things with that. Okay, so what I like to do, for instance, is show that you can do some kind of community clustering, but I don't know why here it's not working. So yeah, okay, you need more points. Okay, so what I try to tell you is that if you have a target distribution with 2 points, you can see them as 2 clusters in a way, and if you move that to a distribution where you have communities, usually Gromov will preserve communities because points close together will be mapped onto just a unique point, and points far away will be mapped to far away points. Okay, so this is pretty small problem. The problem is that, of course, if you don't have the proper proportion, things break. Okay, so I'm going to talk to you about that later, but we have ways to handle this kind of thing. Okay. So now, let's come back to graphs. if you look at graph, the way we're going to model graph is the following. 3 aspects. Okay, when you have a graph, you have the structure. Basically, adjacency matrix. You can also use, I don't know, shortest path between the nodes. Okay, so basically here you have a structure where we will suppose that we have an implicit position xi in a space that encode the structure. You have the features on the nodes. So note that I don't use exactly the same notation as Anna. For me, labeled nodes means that I have features on the nodes. Okay, it's not that they are aligned. Okay, I'm never working on a line graph, so I don't have a notation for that at the moment. The thing is, here, so you encode the structure in this part, you encode the features in this part, and I mean, this is a distribution, so you need weights, and so each node also has a weight. Okay, so basically a graph is stored as a pairwise matrix D, the same I'm using in the fused Gromov-Wasserstein, okay, can be adjacency, can be shortest path, can encode other types of structure. F contains the labels, the features on the nodes, and H, the weights of the nodes. So when you don't know, usually you use uniform weights, or you can use normalized degrees, or these kind of things, or if you have complementary information, you can put it here. Okay, so this is how we represent the graph, and now we can do optimal transport between those two graphs, and then we get a plan, okay? And so, for instance, in this very nice paper from Justin Solomon and Gabriel Perret, they show that if you look at a distribution on surfaces, and you compute D as the geodesic distance on the surface, when you map from this to this, so they use entropy, and that's why you see a big blob here, because this is a Dirac, and it's mapped to actually an area on the right. And you can see that it really preserves the structure, okay, like the hand goes to a hand, the top of the head goes to the top of the head, which is very crazy, is that this structure is very far away, but still humanoid in a way, and it still preserves in a totally unsupervised way the structure when you use OT. Okay, and what killed me actually, I mean, when I saw this paper, I was like, this is the future, and I was not doing Gromov at the time, and so you can move from this to this, and it still preserves the overall structure, and I think this was a killer feature, very good to illustrate the strengths of the method. Okay, so this is unlabeled graphs, but you can also work on labeled graphs. So one application we did, so this one was an extension I'm going to talk shortly about, but when you do fMRI on a human doing a given mental task, you have obviously different structure of the brain. Okay, we do have different structure, so you can segment the brain and recover a nice surface of the cortex, and the surface is different between two subjects, and of course in each point of the surface, you have activation related to the functional MRI. Okay, so you have vectors on each of the points of the surface. And what we did was train an optimal transport, optimize it to find a plan that finds correspondences now across subjects. Okay, so correspondences that both respect the surface of the brain, but also respect also the activations. So jointly, and where alpha allows to go from one to the other. And so what we did is we actually use a pair of subjects. We estimate an optimal transport plan on one mental task, so for instance, doing calculations, mathematical calculations. And then we use the plan that we estimated between the two subjects to predict activation onto the second subject on another task. Okay, so basically we take the activation on the subject on the left, and we use the plan to map the activation on the right, and try to see if it works. I mean, if you manage to predict activation, you can have a good alignment between the two, and we were very happy to see that without alignment, so the standard method, they get a Pearson correlation of something to 0.25, which is already quite good. I mean, the brain is noisy, and when we align with Gromov-Wasserstein, you can get up to 10 points in Pearson correlation, because basically you mapped and you took into account both the geometry of the brain and the activations on it. Okay, so the thing is, we do optimal transport here, so we have constraint, okay, which means that we move from one distribution to another one. Those are the marginal constraints I talked to you about, you know, when you sum the column of T, when you sum the lines. this is very strong actually, because sometimes the weight, you're not really sure about them, okay? As I told you, on a graph, if you don't know, you put uniform. So, well, you put something, because you need to be on the simplex, you need to have the same mass on the left and right, but it's not always a good weight in a way, okay? So there are ways to basically relax those constraints, and it's very simple. It's basically now you optimize, so I shouldn't have put it here, it's just T positive. And so now you do still Gromov, but instead of having a hard constraint, you penalize violation of the marginals, okay? And so you have a penalization parameters that tells you how much you accept that you violate the marginals or not. So this is unbalanced, and this was very important, for instance, in the brain, because when we did the brain application, because we each have different areas and different surface of area where we do our work, basically in our brain, and so you need to be able to adapt a little bit to a change of mass if you want to map well. And so you can go the extreme way. So this is something we did with an ex-PhD student, Cédric Vincent Cuaz, where instead of using this where you have lambda, you go the extreme way where you respect exactly the weights on the left, the constraints on the left, and you totally relax on the right, which basically corresponds to reweighting the graph on the right. Okay, so you do Gromov, but you optimize with respect to the weights of the graph on the right. Okay, and a very nice example of this is that basically what it does is that it searches for a subgraph on the right that fits your graph on the left when you do that. Because it's going to reweight, it's going to put zeros on some of the nodes, which means that it's going to select a subpart of this graph. And here you have two communities, three communities. When you do that, basically it's going to just select two of the communities, and that's the optimal semi-realized Gromov-Wasserstein. And you can see you don't have weights here, you don't have a H bar on the right. Okay, so those are variants of Gromov and fused Gromov, and now I'm going to talk to you about what you can do with that in more machine learning, how we can learn from the data using those tools. So basically what you can do, let's take a step back. So it's a very nice mathematical object. We do have some algorithms. I won't talk about the algorithm, but feel free to come and see me. We have tons of them to solve that. So the tool allows you to do different things. So the optimal transport plan is something fascinating because it tells you, oh, this point goes here, this point goes here. So it allows you to interpret, it allows you to map, to transfer information across graph. But you also have a question about the Gromov-Wasserstein geometry, okay? And I'm going to talk to you about that afterwards because it's very fun. And actually, Bharat will talk to you a lot about geometry in the next talk also. And so it also provides you a similarity between graphs, which, you know, in machine learning, you usually minimize a cost, a loss, or whatever, and Gromov-Wasserstein can be a loss, especially if you work on graph data. Okay, so now let's go back to the geometric part, okay? So you all know about the Euclidean barycenter. We already had a lot of talks about Frechet means. Well, now that we have a way to measure similarity between those distributions, you can do a Frechet mean in the fused Gromov-Wasserstein sense. And so the idea is, of course, you search for a pairwise matrix and weights. So the weights can be fixed or not, or you can also, here it's just for Gromov, but you can also put feature matrices here and optimize them together. So the idea is you want to minimize the weighted sum of fused Gromov, and it's going to give you basically some kind of interpolation between different distribution, between different graphs. I'm going to show you examples of this. How do you solve that? Well, you do block coordinate descent. Basically, this is a sum over different optimal transport plans. So you minimize over D, but also all the T for each of the fused. And so you basically update the T, you update the D, you have it in closed form, and then when D is changed, you update the T again, and so you basically decrease the cost at every iteration, and you get somewhere, okay? And so you can compute those, and I'm going to show you an example of those. So here, I take this nice circular graph, I compute 8 noisy versions of this, and then I compute the barycenter of those. Oh, the color here is a signal, okay, it's a 1D value, and this is the barycenter you get. And the nice thing here is that when you compute the barycenter, you select the size, okay? So you can take a barycenter that has barely the same amount of nodes here, but you can also take a smaller one, doing, in a way, compression. You can do that for other structures, so this one is a bit more complex, and if you compute the barycenter, again, you're gonna recover the structure, more or less the signal. So you see you have a bit of here, you lose a little bit of the yellow because of non-perfect alignment, and so since the features are computed by doing averages, when you do the block coordinate, it kind of do a low pass a little bit on the signal, which might be interesting in some application. And so one example of this is that now that you can compute barycenters of those points, you can extend k-means. Okay, so k-means is you take a point, you have clusters, and you compute the distance to the cluster. You, for each point, find the closest cluster by computing the fused, and then each cluster is updated by doing a Fréchet mean of this cluster. And so this is a data set that we have, like with 4 types of graph with 1, 2, 3, and 4 communities. And this is the iteration of our extended k-means. And you see that we do recover this type of graph, so 1, 2, 3, 4 communities. Okay, so you can go beyond that, okay? And you can do what is called dictionary learning on graph, which is a little bit like PCA, but more constrained, simpler in a way. Okay, so now you have a data set of graph, CI, okay? And you want basically a model that can reconstruct your data set CI from an embedding. Okay, so WI is the embedding of the graph, CI is the graph, and you want to reconstruct it. The beauty of this is that Gromov do not need the same number of nodes, okay? So you can fix the size of C, okay, which is exactly what Anna did for regression. You fix the size of C as a fixed number of nodes, okay? And so you can use a simple model, for instance, a linear model, something we proposed, again with Cedric, where you have a linear model here. W's are optimized over the simplex, C are a matrix between 0 and 1, and we try to fit adjacency matrices like this. So when you do that, you optimize over C and W's. So you can do that in a online or stochastic way. And so, for instance, here we have data set with SBMs, you know, stochastic block models. And so these are the representation we have of the W's depending on the class of the graph. And you can see that basically, interestingly, we learn the dictionary where one dictionary corresponds to those, one corresponds to those, and one corresponds to those. So they are all clustered on the corners of the simplex so that you can better reproduce. But you can go beyond that because this is linear. It's very simple, it's very powerful, and easy to fit. But actually, we have a nice geometry here. So you can use this geometry to predict instead of having a linear model, to say my prediction is actually a barycenter weighted by WK. Okay? And if you do that, it's not anymore a linear submanifold on the simplex, a linear simplex, but then you interpolate in the fused Gromov-Wasserstein sense between the different corners of your dictionary. Okay? And so by doing that, basically you can predict a structure, you can predict a graph from an RD vector on the simplex. Okay? So keep that in mind, we're going to come back to it. Okay, so now we did the unsupervised learning, where we go from a data set of graph to a representation in a fixed representation where you can compare all graph. Yeah, small comment here. W is fixed size, W is a simplex. So basically now you represent your graph just as position on this simplex. You can do stuff, you can use a kernel now, you can use, you can do a lot of things, okay? So now we're going to see how we can use optimal transport to do supervised learning. And I mean, I think you can see me coming here. We're going to either use the fused Gromov as a loss when you train, you're going to minimize the error of reconstruction in a way, or you can use the fused Gromov also in a more complex setup, and I'm going to start with that. First, we're going to look at the problem of graph classification. So now you have a data set of graph. Some graphs have, all the graphs are labeled, but you know, a graph level label, okay? So basically it's a molecule, and the label is it going to kill you or not, for instance, okay? So is it poisonous or not? And you want to predict that for new molecules. And so this is a classical problem. There are a lot of methods, okay? I'm not going to tell about all of them, but for a while, and still in some cases, people tend to forget that, graph kernels are state of the art. okay, to measure similarity between graphs, so that you can have after use this kernel to basically train an SVM or whatever you want. And so FGW do not lead to a positive kernel. So that's a problem. If you do exponential of minus FGW, it is not a positive kernel. Well, we did it, okay? Because you can still give it to scikit-learn, and it's going to work, and it's going to work actually quite well. So the math is not rigorous, but it seemed to work. But that was not something we really, are proud of from a mathematical perspective. You can do graph dictionary learning, as I said, and now you are in RD space, and then you can use any kernels, okay? Or nowadays, the trendy way is to do graph neural networks. So how do graph neural networks work? So most of them work on message passing, where you have a graph with features on the nodes, and then what you do is for each node, you pass the values of all the neighbors, then you merge those values, and you update the feature on each of the nodes. That's the message passing part, okay? So each layer, basically, you spread information from your neighbors to the nodes, and you do that for all nodes, okay? And then you have non-linearity, because it's deep learning, and then you do message passing again, and so on and so on. But if you want to do a graph level task, then what you need to do is to go from all those where you have features representation on the nodes to a vector representation, so that you can basically put your last layer on MLP to predict whatever you want to predict. Okay, you don't want to label nodes here, you want to label the whole graph. So what they use usually is they do pooling, it's called, and basically they compute big averages of the features of all the nodes. So you go from a very subtle representation where each node has a lot of information to just computing a mean or a max or these kind of things. And my opinion, and the one of Cedric, was also this is a bit, limited in a way, because when you do this pooling, you might lose a lot of information because you totally forget about the structure. Okay, so what we wanted to do was to look at that, to go from this representation here to a vector representation that takes into account both the node features, but also the structure. And so we propose this, so the name is a mouthful, sorry about that, it's called template-based graph neural network. And so the idea is you still do a graph neural network, okay? So you still do your message passing along the iterations here. But then when the pooling comes, when you need to go from a graph to a vector, instead of just computing an average or doing these kind of things, you can just compute a fused Gromov-Wasserstein distance to templates. Okay? So, and basically, if your point is close to a template, you're going to have a small distance. If it's far away from the template, you're going to have a large distance. So it's a way to use, basically, the fused Gromov geometry to represent where your graph is in this space. Okay? And so you compute the distance to the templates, and the templates are learned by backpropagation, and so you learn the templates so that the distance vector can be used by an MLP to actually predict the final level. Okay, so I'm not gonna lie to you, this is not the fastest GNN, okay? It works well on data set with relatively small graphs, okay? I mean, don't apply it, on Collab or, very large data set, of collaboration where the whole world of the whole scientific world is connected, because it's gonna explode. But still, for graph level task on relatively small graph, it had crazy good performances. So never happened in my life, this is our, and we had black everywhere, and we didn't have to fight that hard to get the black everywhere, and so we really had a gain on everything. It was very, very, very interesting. Also, on this one, we redid everything, with nested cross-validation for all the methods, instead of just reporting performances from the others, which led to also discovery that some methods that people think work very well do not work that well in practice. But the thing was, we really had a gain, and I'm still surprised that 3 years later, we're still ranked very well. Paper with Code is a very nice site where the performances are reported for methods, and we are still first on one data set, and really well, ranked on others. And so I do think it's a very strong method. Of course, it's slow, okay? But we do have the layer implemented in POT. You can put it in a PyTorch geometric, and so it's going to be slow, but it might work extremely well if you have complex graph and you need to really encode the structure. Okay, so I've been a bit fast. So, do you have any questions? Now. Yeah?
Yes, about kernels. So you said, yeah, kernels is still kind of interesting to use with graphs.
Yeah?
Could you use your approach, could you combine your approach with kernels in some way? So here you used a neural network at the end of your using Agaz, but now you could also probably use this vector in kernel methods.
Of course, of course.
And you could use the plan maybe of your optimal transport.
So the thing is, if you use you could use the plan, and it's actually a strategy that's called linear OT. Basically, linear OT is a variant of optimal transport where you take a center distribution and you compute OT for all your data to this center distribution. And by looking at the displacement of this center distribution, you're in the same space and you can compare those displacements. So if everyone goes to the right and everyone goes to the left, they are obviously far away. If everyone goes in the same direction, they are close, you see? So there are ways to do that. Yes, you could. Here you could put a kernel. The thing is, those templates need to be learned. If you take them from the data, it's gonna work, I think, because you know there is this very nice theory about distance-based classifier. Okay, so under some conditions, if the distance is good enough, you can learn a classifier like an SVM. Instead of kernel, you use distances. Okay, so I do think it works. We didn't prove that we have this property. Okay, but I do think it's gonna work if you take data, but you're gonna need a lot of data, and you're gonna need to compute a lot of distances. And I mean, this is what's gonna kill you, because here you can learn a small number of templates, and then compute only a small number of distances. And so if you use the kernel here, how do you train? You know, you need to backpropagate through the kernel, and so maybe you should use an MLP.
Yes, I mean, quick and dirty fix would be to use the backpropagation to find the templates and then try a kernel.
I didn't try it. Maybe that's a good feature, it's a discriminant feature learning, and then you can do kernel and probably uncertainty better. That's a good point. That's a good point. We didn't look into that. Other question? Yes?
On the unsupervised part, would you have a way to describe the random fluctuations between your centroid, so the centroid of your graphs, and the different versions of your graph?
You mean in the k-means?
Yes.
Yeah, I mean, like k-means, you don't. I mean, in k-means, you have... No, you do in a way. You do in a way because you have the centroid. You can compute again the transport, and you can look at the displacement from the centroid to each point. So yes, you can afterwards. Yeah, but no, you don't use it when you train because you just use closest point. But afterwards, you can come back. Yeah, you could use linear OT from the clusters to learn subtleties in each of the clusters.
Yes, but what I mean is that could it help you to build a statistical model or probabilistic model to describe the random fluctuations between your centroid and the instance?
So that's a good point. There were like methods that use a probability that is exponential of minus the fused Gromov. You can simulate those. I've seen a paper doing that. I had the idea, but never get to that. And I've seen a paper doing that. I think it is interesting, but in a way, it's always like a monomodal distribution around the graph. So yes, it will encode in a way the uncertainty, but you know, in an isotropic way, kind of monomodal. I think we need to do better than that on graphs because it's very subtle objects. But yeah, that's a good idea. I think the theory to study, you know, this distribution and this normalization is. I don't want to do that personally, but maybe smarter people will, and I'm going to use their work, which is the good trick when you do ML. Yes.
A quick question about the way you take information from the graphs. I think the reason why people take some simple functions like the mean or the max or the mean is because they have some invariance properties, right? So if they say they rotate the graph or change it in somehow, that those functions stay the same.
Indeed, you need to be a permutation invariant for graph. Okay, but yes, but that's not the reason. I mean, the thing is, there are tons of ways to do permutation invariant stuff. There are more complex one and simplest one. I think they use the simplest, but actually recent work on neural network has shown that go beyond mean, for instance, as distances, or people have, I've seen things where they use the sliced Wasserstein. They use slicing to actually represent the neighbors instead of to represent the whole distribution of the graph, you know, instead of all just one value. It's more powerful in a way. So yes, mean is permutation invariant, but what we propose here is also permutation invariant, because fused is permutation invariant. And yes, it is a requirement. If you're not permutation invariant, your pooling makes no sense. I agree. Okay, so I'm going to get back to the last paper, to the last method, which is something called supervised graph prediction, which Anna called graph regression, I think. No, don't remember exactly, but we have 10 different notations, you know, for the same problem, and that's usually the case. But it's nice to have all the vocabulary. So I'm going to use mine, and then I will let you make the connection. So now what we try to do is to go from anything, okay? So from data to a graph. Okay, we want to train a model that takes something as input and outputs a graph. Okay, so it's supervised learning. We have examples, okay, of inputs and outputs, but we want to go beyond just vector input. Okay, vector or real. We want to go a little bit further than that, and to do that, well, you need non-linearity and you need more complex problem. And so the applications, there are tons of them. So to do knowledge graph extraction, in natural language processing, be able to predict a graph is very important, and molecular identification in chemistry, of course. And so this is actually, you know, for those who did machine learning, this is just structured prediction, okay? It's structured prediction with a specific structure. That is, the structure is the graph, okay? And so how does structured prediction work? Usually, so the traditional way to do structured prediction is to use surrogate method, okay? So the idea is to encode the output in a set, if you want, and to predict a position in this set, and then to decode this position back to the actual object. Okay, so the main idea is predicting a structure is a pain. Okay, it's a discrete object. It's extremely complex. Okay, but if you can find a representation where you have well, Hilbert properties, now you can predict stuff, okay, in an Hilbert space. You can learn function in this Hilbert space. So in this Hilbert space, you can predict the graph in the space, and then you need, in a way, to solve the pre-image, you need to come back to the original graph. So those methods are actually state-of-the-art in many applications, especially molecular identification methods, okay? Basically, if you have a good kernel, well, it's quite unbeatable, I would say. But, I mean, good kernel are hard to come by, especially when you have very large data set. And so after a while, maybe it's interesting to learn representation, which is what people are doing at the moment, like learn representation, but still trying to do that. Okay, but this is very interesting, but the problem with that is that it's actually a bit costly, because in a way, you need to decode. Okay, you need to go from this representation in your space, you need to come back to a graph. And this is a very difficult problem. Okay, so there are tricks. Okay, for instance, when you do molecule identification, you might have, you know, a way to prune. Okay, to say, oh, it's clearly not this one, this one, this one, and to select on a smaller set. But then you still need to compute all the set and find which one is the best. Okay, to decode. And so, of course, Anna talked about linear regression for adjacency matrix. It was a very elegant way to do that also, and that this one has an interest here is that when you predict the adjacency matrix, you're done. You already decoded basically your graph. You just need to do a threshold, and you have your adjacency matrix. Okay, so basically when you do that, the prediction is much more efficient. Okay, so that's what we try to do, and so. In order to do that, we're going to use the barycenter I talked about, okay? And so the idea is to say, well, my predictor, okay, For X, X is an input, okay? It's not a graph, it's something, okay? For it can be a spectrum, you know? And so the predictor is F is actually a barycenter of template graphs, okay? That can be learned, okay? Or that can be taken from the data, where the weights are conditioned by X, okay? And so when you do that, it is not a linear model, okay? It's a non-linear model that uses Gromov-Wasserstein barycenters to predict. And so now you are in this non-linear space, okay? And so this is the way you put the model. And if you want to train it, well, basically, you want to minimize the error of reconstruction of your model to the true graph, and you minimize the empirical risk of this. Okay, and so C bar is a dictionary, it's just now a discriminant dictionary instead of a representation dictionary. Okay? So this works very well, and this has very nice theoretical property because it actually you can show that you can benefit from all the theory of surrogate-based method. So it's a very beautiful paper from Luc Brogamot. Well, I mean, I'm biased, okay, because I was part of this, but I think it was a very nice approach to do that. The problem, and I think you can all see that, is that for every new graph, you need to compute a barycenter. I already told you this can be costly. And then after computing the barycenter, you need to solve another Gromov to compute the loss, okay? So, yeah, this one is a bit slow, okay? I'll be frank. And so we have strategies to do that. So for instance, so you could do that with where basically your CI or all the training data, but it's extremely expensive because you need to compute the barycenter on tons of graphs. So we trained with a neural network, for instance, a few templates, and you can do interesting stuff. For instance, this, where here what I do is I go, so it's an SBM, but with a weird trajectory in 1D, where when you reach 2, you have exactly 2 clusters, you know, and some of the points actually move, you know, to the other clusters. At 2.5, you see two subclusters appearing. At 3, you have exactly 3 clusters, and so you have a continuity, okay, in the SBM. And so we managed to learn something like that. So after discretization, because the prediction is continuous and you use a threshold, after discretization, we get something similar, where you can see this is the prediction, the structure we have as a function of 1, 2, 3, 4, 5. So this is an illustration, but you manage to learn very complex interpolation in the space of graph, and from, you know, X to the space of graph. Okay, yes?
Can you comment on what is the space where C is living and how you solve the minimization?
This?
Yeah.
Or this? Because there are two.
Yes.
This is a barycenter. So we have algorithm to solve the barycenter. It's block coordinate descent.
The C is living in which space?
C, you fix the size. And that's a weird part also. Because barycenter, you need to fix a size, and you say optimize with C being an n times n matrix, but you can choose whatever you want for n. And this is a bit weird because I have a model, but it's basically, the prediction is parameterized by something. So you can have a very large graph or a small graph when you predict. And the true problem is that you don't know the size of the graph. You want to predict it. So that's a huge limit of the model, which we address in the next slides. Thank you very much. I try to, yeah. Okay, so yeah, so I love this paper, but we really have a hard time numerically, basically, to train stuff. It does work, but it's very slow, and it requires a lot of solving of optimal transport problem. And yeah, sorry.
Slow? What do you mean? How slow is it?
Honestly, I don't have orders of magnitude, but it can take, I don't know, from 0.1 second, for instance, per sample. So if you have a very large data set, it can be very, 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 very long. Okay, I mean, and also the thing is, the solver input for exact OT, because here we use exact, we don't regularize. For a reason is that you don't want to spread information. When you predict, you want, you know, high frequency graphs. The exact one does not run on GPU. So basically, there is another overhead that you need to come back and forth.
But we have statistical guarantees.
Yeah, that's what I said. Well, all the theory and statistical guarantee for this. So. Yeah. Okay. I mean, I'm just complaining because we have something after. You know, I love this paper, Florence. Okay, great. Okay, so the thing is, now we want to use, because as we said, we think that the model is very good. We think that the loss to measure error of reconstruction of a graph is a good one. So we want to basically speed things up and scale it, okay? And so there is actually a work in 2022, it's called Relation Former, that does this a bit in the sense that they use all neural networks, okay, to go from an input image to predict a graph that usually give you relationship, you know, between object in the image or this kind of things. Okay, so very specific to images, but the idea is very smart. Is to take an image and then you encode the image as tokens, and then you can decode. And when you decode, you say what your decode are actually nodes, and so you need to predict after from those nodes the relationship between the nodes, and then you have a graph. Okay, and the output is basically a pairwise matrix that tells you adjacency and features on those nodes. Okay, so it kind of worked. The thing we think was a problem of this paper is that there is basically the loss between two graphs is a quadratic problem. Okay, as we said. But what they did is they solve the assignment problem with an Hungarian algorithm. So they basically, you know, solve a linear problem and then they plug their plan in the quadratic loss. Okay, so in a way, when they do that, they lose some information because they don't use the quadratic information to solve the OT plan. So we wanted to go beyond that and to go, say, beyond just images as input. And so that's why we proposed, so with Paul Zakala, what we call the any2graph framework. So the any2graph framework wants to do end-to-end supervised graph prediction, okay, using deep learning. And so the trick is, here you have an input, then you extract a set of features from this input. That's what I said, for instance, tokens. If you have a vision transformer, you get the tokens of your vision transformer. If you have a signal, well, you can filter your signal and just give it, for instance, as also a set of tokens. And then we use a transformer encoder and decoder to go from a set of tokens that have any size to something that is fixed size and that is the maximum number of nodes on the graph. Okay, and so when we do that, after, from those representations, those node embedding, we predict the structure, the features, and this H here, which is, sorry about that, so small problem in the notation. This is not the weight, it's a 0-1 encoding whether the node is active or not. Okay, and we're going to come back to it. And so basically we minimize an optimal transport loss on all the data. And I'm going to say about that, the idea is since you have a max number of nodes, we do padding. We add virtual nodes, like Anna said, so that we always have the same size and we get parallelized stuff in our deep learning method. Okay? And so the thing is, Fuse Gromov here did not work well. And so there was a reason. So I'm going to come back to the whole pipeline. See, this is your target graph. You have two nodes, okay? This is the adjacency matrix, and I'm going to pad it. So I'm going to add H that say, oh, this node and these nodes are active, this one is not. And the values here, we don't care about them. And we will design a loss that actually discard those values, so you do not care about them. From the input, you're going to have f of theta that's going to provide you with a prediction of whether the nodes are active and an adjacency matrix. And basically, we will do the loss between those two here. Okay? Great. Small comment here. So you can also, threshold, and this is your prediction. But what I'm trying to say is that our loss here needs to take into account the fact that the node on the right, you have binary values, and you don't want to penalize any values here. You don't care about the values that are here because you have a 0. Okay, so we want to discard everything from this part from the loss, which cannot be done with traditional Fuse Gromov. Okay, that's why we proposed another loss that I'm gonna explain now. We call it the partially masked Fuse Gromov-Wasserstein. Is that on the left you have a graph predicted by the network. On the right you have the exact graph you want to predict, but padded. And so the idea is to say if you want to discard everything that's predicted, you know, in, oh, sorry, bad direction. I'm going to come back to that. If you want to discard everything here, probably you should weight it by 0. Okay? And what is 0, 1? Well, the masking on the right. Okay? So the trick is you want the H to be the good one. Okay? Obviously, you want the activation to be 0 or 1, the same as on the right and left. But afterwards, you know, the features on the nodes that correspond to points that are masked, you don't care about it. So you can weight by H. Okay? So you weight by the H of the true graph, where the H are binary. But the H on the left is only appearing in this graph. So now it's an asymmetric loss, because one is a prediction from a neural network that is continuous. The other, you do have binary masking, and you can use them as binary weights in your loss. That's why we call it partially masked. Okay? And so it can be solved by conditional gradient. It's going to be n3 log m iteration. So again, we're not going to scale to large graph, but we're doing deep learning, so we scale to very large data sets now, which is always nice. Okay, I'm going to show you an example of this loss. If this is your target graph, so basically you have just two nodes connected. Okay, this is the adjacency matrix, and you have feature F1 and F2. Okay, and if this is the prediction, so the prediction, I put F1, F2, F2, and 1 H, 1 minus H, where H is a it's continuous between 0 and 1, and A, you see, I have A and 1 minus A. Okay, so now I have two values that's going to tell me basically either if I put a 1, it's going to be this node we selected, okay, and I'm going to put a 1 here, or if I put a 0, it's going to be this node that is selected, and I'm going to put a 1 here, and this will be 0. Okay, so basically those two solutions are good because you predict the same graph, and I'm going to show you, it's above here. This is the loss we proposed, and you can see that it's a very smooth version of what's called the edit distance. That is false, you have an error of 1, or you have 0 error. Okay, and so this is obviously far better to optimize than this, and so it is interesting to see that the corners here correspond to exactly this graph in practice. Okay, so that's why you have 0 loss in the corners. Okay, great. So we have an architecture that does that. I already described it, so I won't go into detail, but basically transformer, encoder, decoder, which allows you to fix the number of output nodes, and then you basically classify the node as being active or not, and that's what's going to allow you to have different size of output graphs. And so in terms of application, we did it from color to graph, so from image to graph. You see, this is a coloring graph, and so we want to predict the coloring graph corresponding to this image. This is actually a difficult method, and Relation Former didn't manage to do it at all. Another one, which is a spatial graph, where those are US cities, those are streets, and you want to predict actually the map from the streets, and also on molecules, and we had very, very good performances in terms of edit distance across all modalities. We were very happy to see that. So it works very well in practice, and it basically gave us tons of ideas for the rest, because now we can go from anything to a graph, so we can do some more complex tasks, which I'm going to talk to you a little bit about, but I'm not going to do the conclusion. Basically, I spent 55 minutes trying to sell you on Gromov-Wasserstein. I'm not going to do it one more time. So, well, thank you. If you have any question, there's a few minutes remaining.
Thank you very much for this overview. And so the basic brick is the distance, and then you are developing interesting method, but really the basic brick is this distance. And so it's interesting to know the size you can handle. That is and the time. That is to have in mind more or less yes. what we can do with your toolbox. That is.
If you want to solve a lot of them, up to 100 nodes, you can do it quite efficiently, I would say. We solved fuse Gromov between 10,000 points on the brains, but it takes a while. So you cannot do as much of them. So, you know, you cannot do deep learning on very large graph yet. So that's one of the things we're trying to do with the PhD student, to use deep learning to speed up the Gromov solver. It's still, well, we have to submit it, but it's still early. I'm not going to give you more details.
Any other questions?
You have some constraints on the graph, like it has to be a tree or is it possible to handle it?
So this is a good question. It's something we try to do. We submitted a project to try to do that. I think it's complex, but I think you can devise for graph prediction. You know, for deep learning stuff, we can probably penalize or put more information in the predictor. For Gromov, basically you just give two graphs. So if there are trees, maybe you could design a Gromov that takes into account the fact that it's trees and make them faster. The thing is, between trees, you have a very fast Wasserstein, for instance. So I'm not sure if you have trees, probably you should use Gromov, which is totally overkill. Yes?
Coming back to an earlier discussion, did you try using the plans inside of kernels?
No. No, I did not. How would you do that?
Well, you can treat them as mappings, and then you can do kernel data spaces.
That's what I told you. Linear OT is doing exactly that. You use the plan and you map from, you need to map always from the same one, or else, you know, you cannot compare them. But yes, you could do that. There is a literature. I'm not extremely a big expert on linear OT, but I know that Gabriele Stedel did a version of Gromov, a linear Gromov, which basically correspond to, you know, having a tangent space around the point and everything. It might be interesting. The thing with linear OT is that it's often solved, you know, as a way to speed up computation. But the thing is, if you need to compute pairwise distances, you know, n2 distances, yes, linear OT will be faster because you put everything in the same space. But you still need to solve OT for each of your points. So it's still n3 per graph. So you do win. If you really need the pairwise distances, linear OT is a very good way. It's an approximation, but it could be a very good one, especially if you have a center graph. So yes, people are doing that. They are not. I'm not sure they call it a mapping, but yeah, they use the plan and the displacement, which is the mapping on the points on the graph.
The big advantage is that you can create mini kernels on that. While from
I agree.
distance, it's...
I agree. I didn't do that. This is a I think linear OT community have done that. They just put it in a kernel then, and they can do tests. I'm not sure which works the best because there is some kind of approximation when you do linear OT, especially if you have a very varied data set. You know, the center graph might not be relevant to all of your modes. So that might be the limit. But if you have a quite centered data set, this is the way to go because indeed, then you're Euclidean and you can have fun. Oh. 23 seconds, so yes.
We are on tight schedule. Okay, then let's thank the speaker again.